In this video, I'm going to take a look at another problem from Chapter 11, Exercise 2. Chapter 11, Exercise 2, again, is over calculating compound events. Much more difficult than Exercise 1 on simple events. So let's take a look at Problem 6. What's the probability of getting at least one head on 3 tosses of a coin? So this problem is easily done by using negation rule. You need not use negation rule. It could be done, that is, without negation rule. But negation rule actually turns out to be the easiest approach. So let's break it down here. What's the probability of getting at least one head on 3 tosses of a coin? If we use negation rule, then we first want to figure out the probability of this not occurring. The equation for negation rule, the probability of some event A is equal to 1 minus the probability of not A. And we're going to start there. What's the probability of this not occurring? What's the probability of getting at least one head on 3 tosses of a coin? What's the probability of not getting any heads on 3 tosses of a coin? So let's figure that out. What's the probability of not getting any heads on 3 tosses of a coin? So with that in mind, is this going to be an and problem? Is it going to be an or problem? If we're going to toss a coin 3 times and we don't want any heads, again, is that an and problem? Is that an or problem? What we want to not get any heads is the probability of tails on the first and tails on the second coin toss and tails on the third. If we toss a coin 3 times and we get tails on the first and tails on the second and tails on the third, then we won't have any heads at all. So this would be an and problem. And then the final question would be, are coin tosses dependent or independent? And coin tosses clearly are dependent. Getting tails in the first toss of a coin is not going to have an impact on the probability of getting tails in the second, which is not going to have an impact on the probability of getting tails in the third. Coin tosses are independent. To suggest that they are dependent would be to suggest that a coin has, say, a memory, that the coin is thinking to itself, well, I came up tails on the first toss, and so let's even things out. I'll now come up heads, which of course is ridiculous. So coin tosses are independent probabilities. It's an and problem, and the probabilities are independent. This one doesn't have any impact on this one, doesn't have any impact on this one. So let's just break it down from here. On the first toss of a coin, what's the probability of getting tails? And here we can use the classical theory, favorable over total possible number. The number of favorable outcomes, we actually get tails, would be 1. And well, it's a 2-sided coin, so the total number of possible outcomes would be 2. It's either tails or it's heads. Now notice here, for the classical theory of probability, we're assuming that this accounts for all possible outcomes. I suppose technically there's some small chance that we could toss the coin and it'll land perfectly on its edge, but we're going to ignore extreme possibilities like that. So the probability of getting tails in the first toss would be 1/2. What would be the probability of getting tails on the second toss of a coin? Well, that too would be 1/2. And on the third, well, that too would be 1/2. And for this equation, tails on the first and tails on the second and tails on the third, it's an and problem. The probabilities are independent. We're going to use restricted conjunction, which just has us multiply these. 1/2 times 1/2 times 1/2, which would be 1/8. Now don't forget to plug this back in to negation rule. 1 minus the probability of not A. And that's what we've just calculated. The probability of this not occurring. For this not occurring, we would need all tails. And if that happened, well, we wouldn't have any heads now, would we? So let's plug this back into negation rule. Let's take that and plug it back into here. 1 minus 1/8. And the easiest approach for 1 is 8/8. 8/8 minus 1/8 would obviously be, let me squeeze that in there, 7/8, and that gives us our final answer. So this problem again is most easily done with negation rule. Now you don't have to use negation rule, but this again is the easiest approach. I didn't want to spend a lot of time going over this in a video, but here is problem 6 done without negation rule. And in this case, you've got to go through all logically possible combinations. As you can tell, don't even bother reading through all this. But as you can tell here, without negation rule, things are a lot more complicated. I've also sort of done it chapter 6 style by way of a truth table. It can be either heads or tails, true or false, and then there are 3 unique variables, and not there are 3 coins. And so this gives us a truth table of 8 lines. 7 of those lines have at least 1 head in them. There's only 1 of the 8 lines that doesn't have any tails, tails, and tails. And so negation rule again is the easiest approach.